So good afternoon. I invite you for a 10th lecture of the Computer Architectures course. And today's topic is about operating system calls and calling of subroutines. So basically the basic mechanism which you use to call some functions and so on the level of C programming language, Python, or some another high level language. So we look how this stuff is done on the level of the actual processor and so on. There is one picture as the invitation to our nice countryside. It is area about Tisa rocks, and we start. So what it means to call or invoke some function and so on. You can call the function locally, directly in the given running program. And what is the problem? That if you want to call some subroutine, and it is possible, for example, that the subroutine or function is provided by some library, and you want to call it from some main program or from some another function which you write, then it is necessary that the callee and caller agree on the way how to pass arguments, because those two sides has to understand what are the actual parameters which are provided, or actual arguments which are provided for the parameters of a given function. And there are many different possibilities. One of the simplest one is to pass arguments directly in the registers, but you need to decide on in which registers and in which order. Then you can pass them on the calling stack, or you can use more complex mechanism through the register window. We look at it when we will speak about a Spark architecture in some another lecture about the different processor architectures and their development. This calling convention is in the fact part of ABI. You have application environment API, you probably know it. It is what are the parameters of the functions, how they are used, and so on. This is described on the level, for example, of C language standard and POSIX standard and so on. But then you need to define a binary interface which exactly defines how those order of arguments and so on is mapped directly to the actual binary data which are sent between the program and the function. And it is dependent on the processor architecture. So it is not fully independent. The mechanisms are similar between different families, but basically the actual placement in the registers depend on the features of given processor, and even about on the definition which is usually provided by the designers of the architectures, or sometimes by the designers of compilers and so on. And if we speak about the biggest nightmare of the computer programmers for the application binary interface, then it is x86 architecture, where, for example, on 32-bit Windows, you have this list of standard C call, calling of operating system, but it can be used even for the calling of the functions. Another calling convention, Pascal language calling convention, fast with registers, std call to the library, fast call to speed up the calling, safe call, this call. As you can see, x86 and Windows is really critical. And if there is a single mismatch between the definition of the function in the header files which are used to compile your application and with the actual implementation of that function, then it is highly probable that maybe it will work one time, but then some part of the memory is overwritten or some data are clobbered and so on, and your application crash. So it is not so, it cannot be taken lightly. Okay, and in this case we usually allocate stack frames in the space which allows to provide space for the local or automatic C variables, C language variables, or you can use explicit alloca to allocate this space on the stack. So it is the regular calling of functions. Then we can have a calling of operating system. In the case of operating system, we need to pass a data and the control to the different mode of privilege, because in your application state, in the user mode, you are protected against modification of, for example, page tables or direct accessing on the hardware, because at the moment when you have this rights to modify those hardware level parameters and structures, then in the fact you can access any memory of each other process in the system. And you want to be able to separate user privileges to ensure that web server cannot, even if it crashes, it cannot access system data and so on. So for this reason, it is necessary first for the system call to do the switch. And this means that you can deliver data through register some way, but okay, it is a little different kind of the calling. For example, you cannot directly select address of the routine inside the kernel and call it, because at that moment you can select any function which is there and maintain the system's state. So basically it is necessary somehow to pass all the system calls through the single entry point. We check that you have right for a given call, and then they multiplex what is the actual function or service which you want to invoke. But it is still that you are running on the same computer. But at the moment when you run a program on one computer and want to invoke the functions which maintain the state of the another computer, then you need to somehow serialize the data, because still through the system call, if you pass the pointer to the operating system, that it usually can look at the data on the address where the pointer is pointing to in the memory. At the moment when you try to invoke some another some functions or some service on another computer which is on the other end of some communication link, for example Ethernet, then basically it cannot look directly to your memory. So it is necessary somehow to serialize arguments, and then when data are sent back, some reply, it is again necessary to serialize the reply and send it back. And there are many different mechanisms how to invoke the service of another computer. Probably everybody from you knows that you can access HTTP pages. Through HTTP protocol you can access web pages. It is easy. But in the fact it is a remote method procedure invocation, because you use some uniform resource locator address which you pass. Somehow you pack it into the HTTP header, you send it to some server, to some well-known port, and the server acts according to the URL or even some additional parameters after the, usually after the question mark character, and then replies back with some response, which can be a page which is rendered in your system. So it is, even this is a remote method or remote service invocation in the fact. But sometimes you want to manipulate with object in some object database, or you really want to call remote procedures. For example, if you want to implement, for example, a network file system, then it is necessary somehow serialize a request to open file, to reply to the file, and so on. And then we can have this remote procedure call for the object environment. There was defined this common object request broker architecture, or this can be a SOAP architecture or XML-based architecture, and so on. And some of those mechanisms are based on the text format. So basically you serialize data as a text message or text page and so on, or XML, and get the XML back. Some of them use the binary format. And then binary formats has advantage that you do not need to convert all numbers to the decimal or hexadecimal and somehow escape them and so on and send them through the link, but you can send them in the binary format. But for the binary format, there is a problem that both computers has to understand the same encoding of the binary data. So, for example, if you have a big endian and little endian architecture and copy directly contents from the memory, byte by byte, to the another computer, then it is possible that it will not work. And some computer can have a long represented like 32-bit and some another a 64-bit and so on. So at the moment, when you send a binary data, it is necessary to define the protocol and standard how to serialize the data and deserialize data, and both sides has to agree on some mechanism. So for example, for the network, there was defined in the past network order, which was for a historic reason defined as the big endian. But on the other hand, for example, it was for the RPC, Sun RPC. For the common object request broker, you send the data in this endianing which you want, but send with the data information about endianing, and if it doesn't match, then the other side needs to do the byte swapping of the data. Okay, sometimes you can use even those mechanisms which needs to serialize all data or part of the data, even when you want to invoke the method or some service, even on the same computer. For example, if you are using Windows and MS Word, then in such case you can embed, for example, a spreadsheet or some another third-party application data into your document, and when you try to edit it, then it starts in background a process of that another editor or Excel or something like that, and you can use object linking and embedding format to deliver keyboard changes to that another application or events and get back a rendering, and then you store the data in format which is not known to the Word inside the Word as a blob, and you get a VMF vector format data which are shown at that place where are those embedded objects. A similar mechanism is UNO, which is used in the LibreOffice, or on Unix and Linux system for the desktop there is a dbus. It is used, for example, if you want to connect a drive or some another component to the system. So it is used for those maintenance of the desktop on the Linux, for example. Okay, so first, if you look into the memory, we have already seen that usually the memory starts from 0, or minimally the address space of the process starts from the 0. Maybe that there is some gap, we get to that little later, and it grows with addresses up, and then there are somewhere places where peripherals are mapped. We have already looked how the peripherals are mapped. But when you build a higher level language or environment, then you want to somehow organize your memory, and it is usually organized such way that we start with the program code, and for the historical reasons, this program code is called as the text section, actual text of the recipe which should be interpreted by the processor, so it is program. Then there is a block of initialized data, so those are those data when you write something in the C, for example, like int global variable g is equal to some value. So if you write something like that, then it falls into the global data section. Then you can have there BSS, which is historical name for the section. For uninitialized data, it is called this way because it is block starting by symbol. So it is that label from the assembly, from the assembly writing of the programs. And okay, so it is the BSS. And in the case of the C language, in the fact, uninitialized data are defined by the specification that they are initialized to the zeros. So even that name little mismatch, it is the area which is initialized to the 0. And then you have there usually some area which is relatively free, which is not directly used or declared to be used during the program computation. And usually, at the end of the RAM, there is a stack which holds the automatic variables and which usually grows down to the lower addresses. And then you have there a rest of the memory which is used as the heap, which is used for the dynamic allocation. So if you do a malloc, then operating system usually increase the area which is accessible to your program, and you allocate blocks of the memory from the heap. And if we do analysis of some executable format of the programs, then you can find that those section has two addresses here. One is called virtual memory address, VMA, and it is the address where a running program sees a given section. And then there is a load memory address, which can be different, and it is where data are stored during the load of the program to the memory or to the flash and so on. On some microcontrollers, for example, you store the initialized data to the flash, which is somewhere else, and then at the program start, it is copied to the actual RAM area. Okay. And usually the minimum start of environment which allows to run the C code on a given processor needs to set stack pointer somewhere, because if you want to call the function, then the stack pointer has to be defined, and maybe it is necessary to set global pointer, for example. So this is that CRT local, CRT0 local S, which you can find in my examples for QTR vsim if we want to call real C main program. Okay. So it was for the bare metal system or some simple system where you have directly mapped the physical memory to the address space. In the case of processes in the Linux kernel, then in the 32-bit case on x86, we divide the virtual address space which is provided to the given program to part which is not accessible to program. It is usually 1 gigabyte of those upper addresses around the FFFFF. And this is used by the operating system. And then the rest of the address space is managed through the memory management unit on the page's granularity. Usually at the start there is some area which is not mapped. So if you attempt to access a null pointer, then you get that well-known segmentation fault or some another information that you access the area which is not available to the program, that there is something incorrect. Then there is usually mapped actual executable file, and there is a mapped a text segment again. So it is the same like in the previous example. Then there is data segment and a BSS. But BSS is usually not stored in the program binary because it is only said that the area should be allocated but not loaded, because if you want to load a whole uninitialized area with the zeros, then in the fact it is simpler for the operating system to fill the zeros there when the program starts. And then there is usually a stack which is somewhere in the upper 1/3 of the program address space. It grows down, and there is a mechanism that it can extend if there is not enough pages mapped to the stack area. Then there is a heap, which basically for a small allocation grows up, but then there is area where mmap and the anonymous memory is mapped. So this can be a little random. And in this area are mapped even if you open the libraries, and those libraries are mapped there, stack areas for the additional threads and so on. So basically it is dynamically managed. By default there is not mapped a memory, so if you try to access the area, then you get the exception. But at the moment when you ask operating system, it maps pages to that area and you can use them. Again, there is one of the possible resources where you can read how it works. And now we return to the calling of subroutine. So the first step, it is necessary to calculate values for those parameters which should be delivered to the subroutine. So it is the first. Calling program calculates what should be put to the function. Then that calling program or calling function needs to prepare that some registers can be overwritten by the calling of subroutine. So you are not guaranteed that all registers will hold the previous value when the calling of the function ends, basically. So you need to be prepared that some so-called clobberable registers will be overwritten by the calling of the subroutine. Then you put the arguments to the or parameters to the function to the correct place, and it can be in the registers or it can be on the stack, or there are some other possibilities how to pass the parameters for different architectures and so on. It is defined by this application binary interface and calling convention standards for each architecture. Then you transfer the actual control to the called function, and the subroutine starts to execute. Why we want to have subroutines at all? The one option is that we want to use the same functionality from more places. So it is one of the reasons. Other one is that the function can be provided by someone else and so on. So this is, we are in the function, and that function or subroutine has to store somewhere values of those registers which are defined as call saved or non-clobberable. So those registers which are agreed that will be in the same state after the subroutine ends as was at its entry has to be preserved by the callee. It is done usually such way that it allocates the space to save those variables on the stack, and even this space is used for the local variables. So if you write a declaration of the variable directly inside a function, then it usually is allocated on the stack. And then the actual body, actual functionality, which is provided by the function, is executed, and results of the execution are placed in some registers. And in which one it is again given by the calling convention for a given architecture. And then it is necessary to restore the previous state of those non-clobberable registers. And last step from the point of view of the subroutine is that it returns back the control to the program which invoke a given subroutine. And usually that caller of the subroutine needs to clean the stack or some space which it prepares for the arguments. We see that later. Okay. And this year we start with RISC-V in our lectures as a main architecture. I have spoken about RISC-V already 5 or 7 years ago, but it was only the example. Now it is our main architecture. So how it looks like for RISC-V when we want to call the function. There are two registers, A0 and A1, which are used as the arguments of the function, but even they hold the result. In some other architectures, another registers V0 and V1 are used to hold the result. And if we speak about those A and V and T registers and so on, there are in the fact only the alias to the registers in the general purpose register file. So in the case of RISC-V, it is registers X10 and X11. Then there are up to 8, in together up to 8 arguments which can be passed in the registers. So they are passed in those additional registers. Then we have there a temporary registers which can be clobbered. This means that if we want to compute something, we can use them. But at the moment when we call some subroutine, we are not guaranteed that the value will be preserved. It is possible that it is overwritten. So it can be used for the temporary. Then for local variables or another information which should survive a calling of the subroutine, we can use non-clobberable registers, and again it is mapping for the RISC-V. Because RISC-V allows only to offset by 12 bits to the pointer, then for this reason we have a problem where to place a global data if we do not want to place them starting from the 0 address. So for this reason, one register is used as a global static pointer which points to the area where global variables are stored in the memory. So it is global pointer, and then we need a stack pointer, which is in the register X2, which is used to define a place top of the stack to allocate the automatic variables and additional arguments and so on. And then we sometimes can use the register S0 as a frame pointer. So this means it is a local pointer which points to the area where a local variable starts for a given subroutine. That you do not need to compute it again and again from the stack pointer. So for this reason, one register can have, it is optional, can have this function of the frame pointer. And then we need a return address register, which is x1 for the RISC-V, which allows to return when we call the subroutine. And then we have the 0 register, which is register x0, which provides a 0 constant and can be used as a discard register. There is, for your information, how it looks on the MIPS. It is similar, except that the return results from the function, it does not overlap the arguments for some reason. But in the RISC-V, they decide that usually, if you call the function, that in the fact the result from that function is usually again the argument to another function. So it is better to override the argument 0 and 1 registers with the result of the function. So there is a difference. There are temporary registers. 2 registers are reserved for operating system. It is not necessary on RISC-V because it has that scratch register when we look at the exception handling and so on. So it is little different, and return address register is 31 on the MIPS, and it is hard code on the RISC-V. In the fact, it is not hard code because we have a possibility to select what would be a return address register, but a default one is X1. Okay, so how it looks when you want to call a subroutine. We use a jump and link instruction, and then we specify the address defined by the label where a given subroutine starts. And in the case of RISC-V, the destination register where we want to store a return address is not fixed by the hardware, but it is possible to select where we want to store the return address. But default, or that one which is used most often, is return address register. And when we call the subroutine, then the following address of the following instruction after the jump and link is stored to the return address register. And then the program counter is filled by the address of the first instruction in the called subroutine. Then a subroutine runs, and when we want to return, then we use in the fact here a return opcode, which is quite often used, this name. But in the fact, this return opcode or return instruction is in the fact pseudo instruction, which provides information that we should, and I have there a mistake, there should be a X1, that is its jump and link to the register, but result of this jump and link should be discarded through the register 0, and we should end at the address which has been previously stored to the X1. So it is in the fact jump to the address in the register, which is a return address register. Return address register is low to the program counter, and we can continue from this previous address after the call of the jump and link function to the function. The same instruction can be used even to implement some branches, some case tables, and so on. So those instructions are defined, and on the RISC-V they are really defined to be really generic. So it is possible to build many different structures and control structures from those instructions. Anyway. Okay, I try to describe why we need a special instruction, or what is the problem of the calling a subroutine. If you have only the instruction which allows to set the program counter to some target address, and you have there a subroutine, then when this subroutine ends, you do not know where to continue. Because if you branch after the instruction which invokes the subroutine directly, explicitly here, then it works if you call the subroutine once. But when you call it from the different location, then in the fact you do not return after that next invocation, but instead you would return back after the first invocation. So hard-coding the branch back from the subroutine is problematic. So one option is that you can set some register and then branch to the register and so on. But if you have a function which provides that mechanism jump and link, then this instruction provides you and moves you to the start of the subroutine, then a subroutine is running, and because a jump and link first store to the return address register the address of this label after the call in the first call, then we return where we should return, and the next time to the return address is stored this address after the jump and link instruction, and we return where it is expected. So it is mechanism as we expect that it should work. Okay, the actual implementation in the RISC-V would look something like this. So there is a branch from this address to this address, and it looks like a jump and link to the simple address, this address of this label. So this label defines the address, which is in the fact this address. And in the instruction is not encode the whole 32-bit address because it would not fit into the 32-bit instruction, but it is encode the offset of the target of the branch. So you can branch this way only in the range of plus minus 2 power 20 in the fact, because you have 20-bit immediate operand, but because you cannot branch or jump and link to the addresses which are odd, then in the fact we can use that 1 bit more for the target address. So it is plus minus 2 to 20. So it is in the fact something like 1 megabyte into the plus and minus. If you have some code which is further than this distance, then it is necessary to first load the address of that function to some register and then call it through the address in the register. So actual instruction is encode this way. It is this and it should not be FF, but it should be 111. I have there some mistakes. So it is binary encoding. Then there is a 5-bit for the destination register. So in the fact it is possible to select a different register to store the address after the branch instruction than the return address register, but typical is that return address register X1. And a program counter is modified to point to the address program counter plus target address. It is much more clean and easy than on the MIPS. MIPS has little more complex rules for the calling. And we have there a design of our processor as we have seen it at the end of the lecture 5, our pipelined version. But if you look at this design, then we can compute there a branch address. You see that we can compute it. In the fact, if we record all 20 bits, then we can have that 20-bit offset. It is no problem. It adds the address to the program counter, and we compute a new address from which we should continue forward. But if we do it this way, we have there a missing option to store somewhere a previous value of the program counter, so this value should be somewhere preserved somehow, because we want to store it into the return address register, and we do not have their option to branch to the address for a jump and link to register, which needs to branch to the address which is provided by the arithmetic logic unit. So if we look at this, we basically need to extend out multiplexer for more options, and in the fact ensure that we can select that we want to branch to the okay, it is same for the jump and link and branch, but we sometimes want to branch to the address which is result of the computation on the arithmetic logic unit. So jump to register, we need to add this path, and we want to add the path from program counter, which allows to store the program counter and send it to the destination register. So basically we need to add there a multiplex. And we sometimes want to add the constant to some register, to program counter, and compute it through the register, through the arithmetic logic unit. So we need to add there another multiplexer and take the address, program counter address here, and use it here. So this is necessary for the jump and link to the register. This is necessary for both jump and link to the register and the jump and link. And okay, and this is necessary for jump and link to the register. So we have our simulator, and it provides those capabilities. So we can look at actual execution of the jump and link instruction from that above example. So what it means, if we want to do a jump and link, when this information gets to the memory stage, then we have got already the target address, which is sum of the PC address. First, in the execute state, there was compute the address, new address for the PC from the actual address of this instruction, and the offset from immediate here. And then when it gets to the memory stage, then we switch this multiplexer and select that we want to branch to the new address, which is computed here. And there is important thing that this multiplexer, additional multiplexer, delivers the PC+4 address to the destination register, so to this X1 register. And it goes there, and in the next clock cycle, it would be provided and returns to the register file. And because we do this, multiplexing here before a forwarding path, then even if you directly use X1 in the following instruction, then it is not a problem because the forwarding can be set up. So this works even. So it is not necessary to put there stalls if we want to use directly the X1 in the next clock cycle. And at the moment, but usually you do not need it anyway, because at the moment when you change the target address, if you do not have there a prediction which already fills you with the instruction from the target address, then you usually need to flush those instructions anyway, so you do not have a problem with forwarding. But if you have a predictor, and predictor predicts the target address and branching correctly, then you can have there already the instruction from the destination of the branch. but we do not have the predictor in this picture. Then there is a jump and link to the register, and okay, and there is this incorrect. No. It selects the immediate operand, and it should select there the program counter. So it selects the program counter, and no, it is correct. Excuse me, no. It was program. It is, in this case, we select a register. Yes, we select a register. In this fact, we want to branch to the address which is in the register X7, and X7 was added by the previous instruction. So in this case, we need to forward the value, the result from here. We forward here to the as a one input of the arithmetic logic unit. Another input is in this case 0, because we have 0 offset in jump and link. And then there is computed the target address. And it is again the same as for the previous example. So we have there the target address, but in this case it is not computed here, but it is computed on the arithmetic logic unit. And at the next clock cycle, the jump and link instruction advances to the memory stage, and we select yes, it is a branch instruction. We select there that the address is not given of the branch by this other for the branches, but that it is given by the main arithmetic logic unit. We select that the next PC should not be that PC previous PC plus 4, but that it should be a new value of the PC provided from the mem stage. And we pass this address, the PC plus 4 of so in the fact address of the next instruction, we pass to the destination register, so to this X1. So when you want to return from the subroutine, then you do a jump register to the return address, and you are again at the instruction address after the calling the subroutine. I hope that every one of you knows that you want to call the functions, and generally how the functions in the C language or C# or Python, how they work. It is basic knowledge. So this is how it works really in the on the actual processor, on the hardware, which we try to analyze here and understand to that. Okay, and then we have there a simple leaf node function example, and it is the leaf node means that it is a function which doesn't call the another function. So it is a little simpler. If it is a function which doesn't call another function, then we do not need to take care, for example, about clobbering of the registers inside the function and so on. And in this case, the function has 4 arguments or 4 parameters, which are filled by 4 arguments, and they are placed, mapped to the register A0 to A3, again according to the standard. And we, for some reasons, we decide that we do not directly compute a result in the A0, but we compute it in S0, but it is non-clobberable register, so there will be a problem. And at the end, the actual value is returned in the A0, which is clobberable register and which is used on the RISC-V to return the result from the function. Up to on 32-bit RISC-V version, we can return up to 64 bits because we have A0, A1. If we want to return more or longer data structure and so on, we need to allocate the space and add there a hidden argument with the pointer to the place where a returned value should be stored. On the 64-bit implementation, we can return up to 128 bits of data directly in the registers. Okay. So now the actual calling of our function. So there is our function. Its implementation is simple. We add A0 and A1 and put the result to the T0. Then we add the another two argument 3, which is J and I and J, okay. And then we do the subtraction, this one, and the result in this case is stored to the S0. And then we return, we need to set the A0 to the return value, and then we return from the subroutine. So it is the implementation of the subroutine. And if we look at the if we look into the implementation of the calling of the function, then we should put there 2, 3, 4, 5. So we put the actual values of the arguments to the argument registers, call the function, and then there can be some following instruction. For example, in this case, S0 is probably not a good option. Maybe it can be that it stores the result of the function to the S0. So it would be A0 to S0 and so on. So we can do what we want to do. But we have not follow rules here, because it is defined that when we call the subroutine, that it cannot, or at the return, all the non-collaborable registers should have the actually same value as was there at the start of the function. So in the fact, we have rewritten the S0, and this can mean that we have rewritten the value of some local variable of the main program, for example. So what we can do with it, we can use a stack. So there is a mechanism how to store registers or values which should be preserved. So this is actually our function, still the same, you see the same body. But in this case, we first allocate a space on the stack, this way that we have left grow a stack by 4 bytes lower. So in this case, there is stack pointer SP pointing to some location. We have subtract 4, so now there is new SP value which points somewhere where is our new space allocated on the stack. We store the previous value of the safe register here. So the previous S0 is stored. Then we execute the code. At the end, the S0 is copied to the A0, so we do not need longer S0 value. And we load back a value from the stack to the S0 register, and then add a 4 to the stack pointer, so our stack pointer is moved back, and we unallocate this space from the stack. And we return from our subroutine. And this way we can implement the nested calling of subroutines that we do not overwrite non-collaborative registers. Now we try to look at the factorial function. Factorial function can be implemented easily a non-recursive way, but for our case, to understand how it works, with the recursive implementation, we define that our implementation will be recursive. So what it means, we call the function factorial, and factorial check if it is called with, for example, argument 0 or 1, and if it is, then it goes out, so it ends. In the other case, it calls again the factorial with modified input argument. And what happens here? When we first call the factorial, the R return address register has been set to the value pointing after the calling of the factorial function. But when we call again the factorial from the factorial, then in the fact a return address is set to this address after the recursive call of the factorial. So what happens when we try to return here from the factorial, when we reach that we should return that basically the argument is 0 or something like that. At this moment, we return there, and we start to return there infinitely. So in the fact, we have there an infinite loop, and we never return back to the actual main function where the which calls the factorial function. So we see that it is necessary somehow to preserve the previous value of the return address register before we call some another function from our function. So if it is non-leaf function, then there is the example for the factorial. So our factorial is implemented if the value is smaller than 1, then we return 1. In another case, we return n multiplied by factorial n minus 1. And the n is input argument, so it is in A0, and on RISC-V even the return value is in the A0, so it is a little simpler than on the MIPS. So what we can do, we can create a space on the stack. So if there is somewhere a stack, there is F, 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 and we have there SP, and it points somewhere. Then we move the stack pointer down by the 8, so it is SP with apostrophe, points here. And then there are two locations. And we store, for example, on this one, we store the previous argument, so n, and on this one, we store a return address. And we check if it is smaller than 1. If it is small, if it is not, then we branch here. If it is smaller, then we set 1 to the A0 and return stack back to the previous location and the return. So basically this is the sentinel. This is where we end after we subtract all values up to the 0 in the fact from the input argument. Now if it is not the 0 at that argument, then we know that it is stored on the stack, and we subtract 1 from the argument and again call the factorial function. But factorial function in this case stores onto the stack return address and n minus 1. And so on, till there is stored 1 return address and n, which is equal to 1. And in this case, or no, n equals 0. In this case, the 1 is returned, and at this moment, the return address basically points to those. After this recursive call, we load a previous value of the n and so on from the stack. We can restore a return address from the stack. We can, and we read the n not to the A0, but to the T0. We can even remove the space on the stack, so we move each time when we return from the recursion, we move one stack frame up, and then there is actual multiplication of A0 by T0, so by the previous n value, and we return. And it would go such long as we get to that location where the return address is not pointing inside the inside, and it should be RISC-V. Up to the return address doesn't point there, but points to that calling function somewhere else in the program, and this break a return from the recursion, and program behaves like it should. Okay, so we have seen calling convention and application binary interface. For RISC-V, it is relatively easy, and it defines that there are some registers and some areas which are preserved, so they are non-clobberable, so they has to be stored to the stack by the start prologue of the function. And then there are some areas which are not preserved when you call the subroutine. So, for example, if you call the subroutine, then temporary registers, argument registers, and the stack area below your stack pointer on the lower addresses can be rewritten by the called function. On the other hand, the stack area from your stack pointer up is yours, so nobody can modify it. Stack pointer from the return from the subroutine has to be set to the same address at which it has been during the calling. Return address register has to preserve what you have stored in the return address register, it is to return to your function, so it is what has been there stored at the time when you call the subroutine, and then those registers are guaranteed that the value will be preserved through the calling of the subroutine. So if you look onto the stack, then in the fact before the calling of subroutine, you have there your stack frame, you prepare the arguments there. If they are more arguments than the 8. So in the case of RISC-V, the first 8 arguments, or if you have some smaller arguments, for example, some structure which holds 2 characters, then it is possible somehow to pack there more of those. But first 8 arguments are passed in the registers, and the rest is passed through the stack. So if we do not fit there with their argument 10 and 9, we do not fit into those 8 argument registers. So the calling program first prepares some frame on the stack, prepares the value 10 and stores it onto the stack. Then it prepares another value, store it onto the stack, and so on, somehow at correct offset. And then it sets argument registers and calls a subroutine. And subroutine stores onto the stack a return address register. And then it stores there those safe registers which needs to be preserved till the end of the subroutine. And if there are some local variables, then there are stored even the local variables onto the stack. And this is example how to call the complex function. And in this case, we call the function, and this function can take the first arguments from the argument registers and the additional arguments it takes from the stack. Okay, so it was for the calling on the RISC-V architecture. Now we look very shortly on x86 in 32-bit mode and 64-bit mode, because this is architecture which you quite often use. In this case, we have only 8 general-purpose registers. They can be accessed as the 32-bit AAX, ABX, ECX, EDX, and so on registers. Some of them, all of them can be accessed even as the 16-bit, because originally the x86 was in the fact 16-bit extension of the 8-bit processor. So some of those registers can be accessed as by half as the 8-bit. So it is quite non-orthogonal architecture. And in this case, one register is again defined as the stack pointer. This is base pointer is in the fact same as our frame pointer for the other architectures. Then there are 2 registers which are usually used for indexing. This one is sometimes used even for the dynamic stuff for the position independent code. So in the fact, number of usable registers on the x86 architectures is very low. And there is complication with segments and so on. But what is important that there is extended IP, 32-bit IP pointer, which is in the fact same as program counter. So very quickly we go through the calling and through the syntax. Problem is that for the x86, there exists more syntax how to write the assembly language. This is the one proposed by the Intel company, and it assigned from the right to the left, same or similar like it is in our RISC-V assembly. But because the instruction can combine access to the memory with computation, there are a different way how to specify the access to the memories by these brackets and so on. And there is a historical syntax which goes from the original Unix creators which use AT&T syntax, and it assigns from the left to the right. And you see that in this case, the immediate value is not marked. In this case, it is marked by the dollar character, and the registers in this case are preceded by the mark, percentage mark. In this case, there can be a clash between the name of the variable, which is some address in the memory, and the register name. So this Intel syntax in the fact is more problematic for such alias and collision in the naming. And there are addressing mode, and as you can see, for example, there is addressing mode where you can take the value from one register, add the value in another register multiplied by 2, and use it as the address to the memory, and the result of this complex addressing can be directly used, for example, for the addition. So it is much more complex. It is not a RISC architecture initially. Today, internally, it translates those complex instructions into the RISC-like micro operations. Okay, there are some examples how you can, for example, load the address data from some relatively complex defined address. So it is offset -8 from the address defined by the one register plus another register multiplied by 4, and the result is put to AAX. We can load this way from the EBX -4 something, from ECX. There is even possible to compute the result of the addressing and store it to the register. So you can use this complex addressing mode, but not the access actual memory, but store the result into the register, and so on. So those are the options. And in the fact, originally operations to load the address are only those which can be used as 3-operand implementation or instruction to add 2 registers and so on. So it is little complicated. Anyway, for the x86, it is defined for the Unix calling convention, not for this Babylon of Windows. It is defined that those 3 registers are clobberable, AAX, ECX, EDX. Those other registers preserve the value, and EBP, ESP are predefined. EBX is sometimes used for the global offset table, but it is preserved anyway, so it is no problem. So 3 registers which are available for the actual computation inside the subroutine are usually not enough. You can get something from those ESP, so maybe 5, but still it is not enough. Result is returned in the AAX if it is only 32-bit. If you need up to 64-bit result, it is stored in the pair EAX, EDX. EDX holds a most significant part. All the calling parameters and so on is stored on the stack. So there is a difference. There is by default, the default calling convention doesn't pass any arguments in the register. So it is in the fact more complicated and usually slower because you need to store the data to the memory. They in the fact are not stored in the memory because they are usually used before you really propagate the data to the memory. So they are usually loaded from the write-back buffers and so on, but it is problematic. And anyway, now we can look what happens when we call the subroutine. So we have there our main function. We want to call the subroutine with the argument 3, and this function only returns actually what is given as the argument. So it is very simple function. And if we look in the assembly, then what happens? In the main function, we first push a EBP onto the stack for some reason. Then we, so this push instruction stores the value in the fact first moves the EBP down and then stores the value on the given address. So it allocates and pushes onto the stack directly. We do not have a push instruction directly on the RISC-V. Then we have there a move which stores into the EBP register the value of the stack pointer. So in the fact we have put the index into the stack where our frame starts. Then we subtract, in this case, for example, 8 for some reason, and do the end. We want to speed up calling of the subroutines. We want to align the stack. So for this reason, there is alignment of the stack. So we align it that it is aligned to the 8 bytes. In the fact, or 16 bytes. Then we subtract the 16 to make some space there on the stack. And into this already allocated space, we can store this 3. So in the fact, we have stored the argument directly, or parameter for given argument directly onto the stack. And then we do a call, and in this case, there is a special function called. In the fact, on the RISC-V, there is a pseudo operation which is called a call as well. So I think that you can use it even in the assembly as well. But it is on the RISC-V, it is internally jump and link. Here it is directly the instruction which calls. And in this case, that instruction doesn't store a return address in the special register, but directly pushes the return address onto the stack. So ESP is moved here and automatically by the calling the function. And usually the function starts with the building stack frame. It is not necessary. You can save omit frame pointer to the compiler, and in this case it would not do this mechanism. But in this case it pushes again a EBP, so it moves the stack down. It sets again a ESP to EBP. And if we want to access the argument, then we know that at our address is previous EBP. Address +4 is the automatically stored IP or program counter, and +8 is the value which has been passed to the function. So we can put it to AAX, which is a return register, and then we need to leave the subroutine, and it is possible to do by this combination of two instructions, EBP to ESP, then pop EBP, and last one is return, where this return instruction pops the value of EEP and returns the execution after the call instruction. Okay, now if we have two arguments and we want function which sums those two arguments, then we again create the space on the stack, then we put the arguments to the stack, and we start from the on the lowest address, we start on the leftmost argument, and so on. So we know that the first argument here is in the fact each time if we start the function by this building of the frames through the EBP and ESP, we know that the first argument is each time at the address EBP +8. And EBP +12 is the second, and we can use directly the instruction which does the sum of the value on the in the stack in the fact together with the value in EAX register, which has been read here, and we leave the subroutine. And actual main function then use the leave as well, which restores the stack location to that one which was there before the calling the main. And the thing starts to be much more complex, where you have a function which a variable number of the arguments, which is a feature which is provided by the C. So in this case, you can put not only variable numbers, but even variable number of types of the arguments of different kinds to the function. And you know probably Printf is one of such functions, which is quite often used. But in this case, we try to implement there a much simple function which gets a variable number of arguments which are ended by a -1 value, and it prepares those arguments, allocates the memory for this, and builds the array from those elements. This function is not much usable because in the real world application you probably would not want to pass this into the function and so on, because you can define the array directly as the initiator of the array. But this is a good example how to work with a variable number of arguments. So we know that this function at least starts with one integer argument. This is that first one. So and it can be even if there are no data in the fact, it would be a -1. So we declare the type that it is it starts with the integer, and then ellipses that there can be more arguments. We call the function which these arguments which we want to use. It is finished by -1, and then there is a code which checks that we have really created array which we want for those arguments. And what we do in the function? In the function, we first need to declare the variable which allows to iterate over the arguments. And in the C, if you include the stdarg header file, then you can use the special type which is called a VA list. So it means variable arguments list. And it works a little like a pointer. So we declare this variable. Then we need to allocate the size of the array, and we do not know it in this case. So in this case, we allocate some maximum size which we expect that the array can have. Then we start to iterate. We know that the first is the argument 0. And we say, okay, we want to start from this argument, from this A. So we say, okay, A is our first argument. Then we check, is A bigger than 0? Or, okay, bigger than the 0. And we are not still fill the whole array. We do not exceed the capacity. Then in such case, we store the A into the array on a given location and increment number inside the array. So we have allocated the array and copied the first element to the array. And we ask, what is the next argument after this argument? And we know that it is integer in this case. So we say variable argument next argument from the given argument pointer, and it is integer type. And this way we can enumerate as long as we get to -1. And we copy the data to the allocated array. And for example, in this case, we put -1 to the end of that, even of that allocated array. And then what is important, if we iterate over the arguments, we should finalize the iteration by this VA and macro. And then we return pointer to this array, and we can print it. So it is how we can use stdarg mechanism. And we can look what we can do if we want to know how many arguments are on this input of the function. So in this case, we run the first iteration through the arguments, but in this case, we run this iteration only to compute a number till we reach a -1 or 0 argument. And there is one important thing. You can declare more of those argument iterators in the fact, but never directly copy their values through the equal sign. It can work, but on some architectures it stops work and your program can get to the troubles or can misbehave very hard. So it is necessary, if you want to copy that pointer to the arguments to another instance of this type of the variable argument list, then you need to use a macro va copy, variable argument copy. And then you can use this and iterate through the array the first time, and then you can iterate the second time through the second argument pointer, and in this case you allocate the correct amount of the memory. So be careful, you should know that you need to start the first. If you want to use the argument pointer and copy it to another argument pointer, use VA copy. If you want to access and get to the next location inside the arguments array, you use VA arg. And you should enter all the iteration by VE end. And there is an example how to write a printf. Maybe that you have been interested how a printf is implemented internally. So in the fact, this is very simple implementation of printf. We say that it is a function which starts with the format argument, and then there is a variable list. But usually printf doesn't directly iterate through the arguments, but allows to pass, because there are more combinations when you want to call printf, fprintf, and so on. So for this reason, it wants somehow to pass a list of the arguments to the printf to another function. And it is done in this case such a way that you start the argument list, say that argument list starts at that format argument, then or after that format argument, call, for example, in this case, vprintf, which is again defined by the standard. You provide there the format again, but in this case, you do not pass arguments directly on the stack, but you pass this pointer in the fact, or it is not pointer, it is the structure which allows to access a variable arguments of this function. And then the vprintf process the arguments, prints what is necessary, and so on. Each time when it finds something in the format, then it needs to use a correct varg function, or okay, it is not function, it is macro call, which specifies what is the type which should be extract from the variable argument list, and you can continue. So it is again the example. There is one significant risk if you work with the local variables and arrays on the stack. This is very common buffer overflow error, which you probably know from the operating system security advisories notices and so on. And there is how it is very easy to build such problematic thing. We have there function g, and function g wants to read some input, so it allocates a space for 30 characters. Then you call finput, which is some function which gets a pointer to the stack here, and it calls a function which should not be used at all, getS. It is a function which is in the standard, but it is extremely unsafe function. And what happens there? G creates the stack frame, then it allocates the space for those 30 bytes. It has there some reserve, and it is aligned and so on. Then it puts the argument, yes, EAX, which in the fact EAX is pointer to the stack. Yes, on the stack we have there the stack frame of the function g. Then we create there the space. We point there by the string to some location in the stack. We put on the stack the address to that location. Call the function f, which means that we start EEP, and function usually by its startup codes stores even the EBP. So this is stack of the function f. This calls the function getS, and somebody writes more characters than 30 or 29 in the fact, and then press enter. And what happens? This data are stored onto the stack frame of the function g, but because there is no limit how many characters can be accepted, then you override a previous value of the stack frame of the function g. So everything looks without a problem till you return to the function g. But when the function g starts to return, then in the fact it interprets the bytes characters which are put over the return address as a address where it should return, and you can return in arbitrary location. So you usually cannot select all possible combination of bytes by the characters. If, for example, you cannot have there a new line character 12 code because it would end the line, but still the intruders can find a combination which allows them to gain the control over your program, and you can do even such stuff that you can put there arbitrary values and then ensure that the program jumps to this area and execute something what you really do not want. There is a protection which non-executable stack and so on sometimes in use, but it is still a problem. There are examples with more arguments, how it will look like on the x86. So there is some example how to store more arguments and call the simple function. In this case, simple function only takes the last argument and the first argument and subtract those. And the middle arguments are not used, but it is the example how it looks in the C program for x86 when it is translated. If we look at a 64-bit x86 implementation, then it adds additional 8 registers. So we can have up to 16 registers. Their encoding is a little random, but it is not important. And we can access all registers by byte. Some registers can be accessed even as the 8-bit in the middle, but only some. Then the most of the registers or all registers can be accessed as 16-bit. Okay, 16-bit this way, or as 32-bit, or as 64-bit. And 64-bit are not called EAX but RAX. So it is 64-bit. And for the accesses, when it is accessed as a 32-bit register, then if you store the value, then the rest up to the 64-bit is overwritten by 0. This is to lower the number of dependencies between the instructions. On the other hand, if you access a register as 8-bit or 16-bit, then the rest of the register up to 64-bit is not modified. So it is okay. It is quite complex because it was added with attempt to keep the compatibility. And in this case, the calling convention for Linux, for the Windows, it is more complex. Defines that we have more registers, and that up to 6 arguments can be stored into the registers. So first, 6 integer arguments are passed through the registers, so it is easier to call the subroutines in the fact. And rest is stored to the stack. And for double arguments, those arguments are stored to the XMM registers. Up to 8 first double arguments or floating point arguments are passed through the another registers, where it is easier to work with them. And return value is stored up to 64-bit in the return address, into the RAX register. And if it is longer, then there is passed a hidden pointer to the area. And stack has to be 16-byte aligned. And because you have a problem to iterate through the arguments, if you do not okay, if you want to call the function and you do not know what is the prototype of the function, then it is necessary somehow to declare how many of those XMM registers are in the fact used by the function call to allow the iteration over those then inside the subroutine. So in this case, the RAX has to be set to the number of used XMM registers. It is such complication, but it is necessary because in another case you need to store too much data into the those argument iterators and so on. So this is such complexity. Okay, so it was for the calling of standard functions, and now if you want to call a operating system. So how works operating system? You have your user space application. They call some lower level application like shell or some SSH and compilers and so on. So if you have, for example, graphic development environment, then you call GCC and so on. So those are the standardized lower level functions. Then all those are using shared libraries or some libraries, different libraries. Then the library calls the standard C library, which provides a runtime environment. And this library then pass a request to the operating system kernel, which can be Linux or HURT or BSD. It works same way even on the Windows as well. So, and it is, as I have already said, when we pass data from the user space to kernel space, then it is necessary to switch from the user privileges to the system ones, because system needs to directly modify the registers in the hardware and so on. So in this case, it is necessary to invoke the execution some special way which allows to trap into the kernel and switch the exception, switch the priority. We have seen already this in the previous lecture, how it is for the interrupts. And now we see how it is implemented for the operating system. And operating system internally is connected to the C library, which calls operating system interfaces. And then internally there is upper layer where it is some generic process management and memory management, file system, device control, networking, and the actual page tables manipulation and data structures manipulation, or actual drivers control and so on, which is specific for a given hardware and given architecture, is in those lower level drivers and implementations. And on the Linux kernel, it is little disadvantage maybe that the number of system calls is relatively huge. On the other hand, there is a guarantee from Linus Torvalds that even old program will run on the newer version of Linux system. So even if some system call is already not so much used, it is usually not changed, or the compatibility is preserved and a new one is added. Okay, so number of system calls is quite large in the case of the Linux operating system, for example. Oh, but on Windows it is quite large as well. And there are different kind of subsystems which you need. And we now look what happens in the case. Again, we have seen this same picture when we have spoken about the interrupts. So this is, we are running in user space. We want to call some read, for example, from the serial port. In this case, it is necessary to invoke somehow the exception which switches us to the system mode in the kernel. Kernel check if data are available. If not, it notifies, for example, hardware, or somehow set up the hardware. And then we have seen that we sleep. Other programs are running. Interrupt arrives, which defines and provides the data or provides the information that some DMA has finished the transfer. It release a semaphore which releases the code in the operating system kernel task in the kernel mode. Scheduler defines that this task should continue, and when it wants to return to the user space, it is necessary again to switch the privilege. Deliver a data, check that the user still has the right to access data at given address and so on, and then return to the user space. And how it looks like, there is a definition how this process is implemented. So basically you have your runtime libraries, and they know that they need somehow put data into the registers and into the memory, and then invoke some mechanism which invokes the kernel. On the RISC-V, it was eCall function. On the Intel, it was originally interrupt 80. You see this exception, or in the fact, a syscall operation, but it is called the interrupt and has the number which is used for it. On the newer AMD-based systems, it is the sysenter instruction and so on. On the 64-bit, there is already added the syscall instruction in the fact. And we need to prepare arguments, then switch somehow to the operating system and notify the operating system which service you want to invoke. So it is encoded in some of the registers. Operating system check if it is valid request and delivers the execution to the subsystem which handles given services. It processes the operation and then prepares a return code and switches back to the standard user mode, and usually the C runtime check for the error, and if the errors happens, then there is a wrapper which sets error value. Probably everybody from you knows that there is a error value. You should know that it is there. Okay, so user program calls the wrapper in the glibc or C runtime environment. It invokes the exception or syscall to the system. Syscall handle check if it is valid request and calls the given service routine. And there is a list of basic functions, and you will get a homework number 4, where you will try to find what a given piece of the code, the given binary, is implementing on the x86, and you get a MIPS and RISC assembly dump from those programs. And in the x86 case, for example, the service with a number 1 is service system exit. So in the fact, if you put there exit and the number in the C code, then it invokes this system call. It is implemented inside the kernel here, and in EBX is expected Z value which should be returned by the end of the program when it finish execution. You can have there a read and write operation. Read and write are low-level access to the input-output. So it directly maps to the operating system calls. And what you know that there is a first argument is some file descriptor, FD. So this one is put into EBX. Then into the ECX is put the address where data should be stored in the memory, and EDX the size. Easy, it executes, and in EA6, it returns how many bytes has been usefully written. For the write, or read, okay, written to the user memory, so in the fact, read from the file. For the write, you provide the buffer which should be written to given device. For the open, you provide the address where is a 0 terminated string or sequence of characters, which is file name, then mode, then if it is read-write and so on, and the mode for the creation of the new file. For the close, you need only the single argument. To change the mode of given file, you say which file with the in the textual form as a string, zero terminated string, and which mode should be set, and so on. GetPit, it has no argument because it returns only the value, mount, reboot, and so on. So you can use the syscall this way. So it works such a way that user space application, your program, for example, calls read, the read, for open and for read, the stream operations. It is high level. It is implemented in the libc. It's internally ends with a read function, and it sets the EAX to the some constants, which for given architecture represents a request for the read. You invoke the interrupt 80. It changes the priority to the system, operating system kernel in this entry S. Check if it is if the requested service is inside the limits of the table describing those operations. Find that it is a read syscall, and reads calls the function sysread, which processes the actual read. Then we restore the state, provide the result of the operation, and do iRead to get us back to the user mode. There is global checking, common, and we return to the program, user program. There is a calling convention for the RISC-V. So for RISC-V, we have more registers, so we can put up to, in the fact, 8 arguments, but for Linux kernel, I think that up to 7 is used. And the A, in the fact, A7 is used to specify the operation. It is not seen here. It is A7 is specifies the actual service which we ask for, and the rest of the registers is not modified. So there is an example of Hello World application. You can find a Hello World application in that template template operating system S in the directly in our simulator. This one is a little extended because by default you know that the file handle, open file handle with index 1 is standard output of the program. So you can directly write a hello world to the file descriptor 1, and you know that it goes to the standard output. So in this case, we can say that actual assembly implementation. We put to the A7 that we want to do an operation, right? We put to the A0, okay, it should, yes, S0. So this means that we put there a 1. Then we put there into the A1 the address of this text, hello world. And in this case, it is text defined by this directive, which is not 0 terminated. So this means that if we have the address after the end of the string, then if we subtract those addresses, we get directed the number of the bytes. We put it into the A2 and invoke equal. And if you do this, then on our simulator, but even on real Linux system running on the with the RISC-V processor, the hello world string appears on the terminal. If you want to open some another device, you can use the open. So basically you specify that you want to call open system call in A7. In A0 you select the file name. In A1 that it should be read write and no create in this case. We do equal, we get a 0, we should check if it is not negative, which means that it is a problem, that we cannot open the file. It is simplified here. And we store the value in S0 that we can reuse it later in another calls. If we want to close the terminal, then we again take the value of S0, which is the one from open or Z1, to the A0, and A7 set for the close, do equal, and we have closed the file, and so on. Exit of the program, we select that it should exit with 0, that system call is exit, e-break, and we are done. There is the example even for the MIPS architecture where it is a little different, and it is the first program really from the Linux torvalds which has run on the MIPS architecture. Again, it is exactly this open and write hello world to the serial line. And it is all for today's lecture.